Hello, so in this video I'm going to go through the modelling and simulation of an RC circuit, or known as an resistor capacitor circuit. So in terms of the contents, you can see here, so I'll go through the resistor and capacitor circuits. I'll give you details of the RC circuit. We'll then look at the different forms, so the transfer function form, and then the standard form, and then we'll look at modelling and simulation using Matlab. So after this video, you should be able to explain the following. So how to take a first order differential equation, convert this into transfer function form, and then understand system properties based on the standard form. And then how to then undertake the modelling and simulation in Matlab. So the equation, the ordinary differential equation for the RC circuit is given here, where V subscript in of T is the supply voltage, i.e. the input. The R value here is the resistor, and the C value is the capacitor. And then V subscript out of T is the voltage output. And you can see the circuit diagram here of the RC circuit. So you have here voltage in, current, you've got your resistor here and capacitor in series, and then your voltage out. And also if you want to look at it in terms of the Arduino here that I've got, so I've got a 5-volt supply being applied to the breadboard here, so it makes 5 volts across here. So 5 volts passing through the resistor, and then the voltage thereby then as the input to the capacitor, which will then, the capacitor will effectively be charging based on the voltage input, and it will discharge if you remove the voltage. And then just to complete the circuit, you can see the black wire there going back to the ground. Ignore the blue wire for now. So that's there just to show you what it visually looks like. So we're going to take a model-based design approach. So we're going to look at the theory and also the simulation. So if you recall from the previous slide, we had this here, this first order ordinary differential equation. And what we're going to undertake is the Laplace transformation. So if you recall the Laplace transformation of a first derivative, in this case, you can see the notation is dv out of t over dt is equal to, in this case, s, because d over dt becomes s, and then v out, so v out here, so we're out the subscript of s, so the t effectively is replaced by s. And then you can see the transformation here. Okay, so you can see the transformation of this here applied here. You can see the constants, V in, RS, or RC, sorry, and V out and V out are obviously the same, and you'll see there the T replaced by S and RS, and then that's replaced by the transformation that we just went through. And then V out of S, you can see the T here is replaced by S. What you'll notice is that we've got here common is V out, so you can see here V out is common to both parts. So we can effectively move this outside the bracket as we've done, so here outside a square bracket, just to simplify the equation. And the reason why we do that is because we want to put this equation 1,3, into transfer function form. And transfer function form is given by this form in the case of output over input. So we can algebraically manipulate this equation so it's such that it's V out over V in. So you can see here what I've done effectively is just cross multiply by 1 over V in, and then cross multiply by 1 over RCS plus 1, and hence you end up in this transfer function form given here. So if we consider equation 1,4 that we've just derived, so this equation, the above is already in standard form. So if you recall standard form being k multiplied, where k is your system gain, multiplied by 1 over tau, which is your time constant, multiplied by s plus 1. This is already in standard form, so it's very, very nice for us. Therefore, k is equal to 1, because you notice obviously the numerator value is 1, and we don't effectively have a value outside here, so the system gain is 1, and the time constant, you can see here, is RC, so it's resistor multiplied by the capacitor. So as just a quick example, if we substitute into equation 1,4 the above values, so a 1,000 ohm resistor and 1000 micro farad capacitor, what we'll get is RC equaling to 1. Okay, so if you remember, based on the standard form, and it effectively telling us or informing us in terms of what the system response is going to look like. So the time constant's very useful because it kind of tells us in terms of what's going to happen with the system response that we'll go on to in a minute, and the system gain effectively gives us the final value of the system. So in this case, obviously the system gain is 1, so we expect the final value of the system to be 1, subject to a unit step being applied. Okay, that's key there. So in this case, if we apply a unit step input, that would effectively represent 1 volt. And then tau here, RC is equal to 1, considering this. So this is then going to give us this transfer function. Okay, so a nice to look at transfer function. So 1 over s plus 1, where time constant, as we've just determined, is 1. So if we look at this here, so we look at the table and the system response, we know that this is the case, the output percentage. So we can just write this straight away into the table if we're whatever values we're interested in. So in this case, I've done 0, 62.60, I should say 63.2%. Sorry, a little typo there, and then 95%. And then in terms of the time, the seconds, you know that the time is always going to be, in this case, obviously 0, 0. 63.2% is always going to be tau. 95% is always going to be 3 tau. So in this case, tau is equal to 1. So obviously tau is 1, 3 tau is 3 seconds. So you know that in this particular system, the output percentage, in this case 63.2, is going to be at 1 second, and 95% is going to be at 3 seconds. So now let's look at in terms of the output amplitude, because the output amplitude is very much dependent on the system gain. But in this case, the system gain is a value of 1. So again, 0.632 multiplied by k, obviously k is 1, 0.950 multiplied by k, where k is 1, and it gives us the output values for this particular time value, so 1 second and 3 second. So if we look in terms of what this looks like in terms of a sketch, we can see here 0 seconds, 1 second, 3 seconds. We know at 1 second we're going to be at a value of 0.632, which in this case, because we've got a system gain of 1, it's going to correspond to 63.2% of the output percentage. And in terms of after 3 seconds, we know that this is the value we're going to get in terms of the amplitude is 0.95, and in terms of the output it's volts, and that's going to be at 95% of the output percentage. Okay, we could obviously apply because initially if you saw on the Arduino it was a value of 5, so we could apply maybe 5 over s, and that would just then mean that this value here would be 5, and then you'd have to redo the calculation. So effectively, that's something maybe not to worry about, something you can have a look at in your own time. So in terms of, if we just go back and look at the system gain here, and there's some important points here. So if we increase the resistance or have a higher value for the resistance, this lowers the current, and this results in a larger time constant value. And you think about that, if you're passing a voltage over or a current over a resistor and you increase the resistance, that's going to have effect in terms of, in this case, it's going to result in a larger time constant value. Okay, and you can obviously see by just looking at the simple equation or looking at the time constant. So if we increase the capacitor, so you imagine you increase the capacitor value, this is going to result again in an increased time constant, which is kind of like obvious again, because if you're effectively trying to charge the capacitor, and you increase the capacitance, it's going to then result in a higher time constant, and hence it's going to take longer for the system, for the capacitor to be charged. And likewise if you increase the resistance. So what we can do is, if we want to investigate that relationship further, we can set up a Matlab script. So I've got the usual command here, so clear CLC and close all, just to clear the command window, clear the workspace history, and close any existing open graphs or graphs that are open. So resistor capacitor transfer function. So what you'll see here, this is probably the first line that we might want to go to. So system is equal to TF, so that's the command for transfer function, and then in brackets, numerator, common, denominator, close brackets. And that's effectively our transfer function command. In here, we could actually just straight away, we could just put in the value for the numerator, which in this case you can see I've put up here. Numerator is equal to 1. And denominator here I've put is RC and 1. Okay, because if you remember back to the original equation, it was just simply given by this. So what MATLAB sees is, okay, numerator 1. Okay, that's nice and easy. The denominator is RC1. And because we've got effectively two coefficients there, hence 1, 2, MATLAB will know that that's a first order, well, it's a first order denominator. And then the transfer function command. But like I said, you could straight away just put these in here, but I've just decided to do line by line. Because MATLAB, if you remember, reads top to bottom. So it'll read this value first, read this value, and then it'll populate the system for me. And that'll appear in the workspace. If you look in the workspace, once you run this, you'll see system, and you'll see your transfer function. What I'm initially going to apply is just a step input to the system. So I'm effectively going to apply, if you do step to system, in this case you can see I've called system here, and hence why I've got system there. But if you use the step command, it applies a unit step input. So it means that I'm effectively applying 1 over s to the system. So this is effectively y of s is equal to a unit step input multiplied by the system. Because if you remember, y of s is equal to u of s. And in this case, the notation I've used for the system, because we're just considering the process, is g subscript p of s. That there. So that's there is our equation. That's effectively, when we say step, we're applying a step input to this transfer function. Right, so graphical output. Usual command to set like the graphical area to font size 20, X label time. Because we're applying this step input here, MATLAB by default will always put seconds for some reason in the X label, and then Y label voltage. Okay, and then in brackets I've just put what the unit is, so volt. Grid on, so put a grid on, and then hold or. Okay, so I'll explain these commands now. Because what we're doing is we're effectively simulating different RC values, so resistor capacitor values. I'm not going to tell you how these resistor capacitor values were made up, because obviously you can do the calculations in your own time. But what I've done is I've done RC, so resistor capacitor, is equal to 0.5, so 0.5, all the way up to 3. But I've done these in intervals of 0.5. So it's going to be 0.5, 1, 1.5, 2, 2.5, and 3. So I've effectively running this transfer function with 6 different values of RC. Okay, here RC. And whenever you do one of these 4 commands here, you also need to include an end command here. So for these 6 different values that I'm simulating through this transfer function, subject to the unit step input, that's effectively what I'm doing. I'm running 6 different simulations. Okay, and that's why I've got this hold all command here. Because what it does is it simulates 1, holds the result, simulates a second, holds the result, and then carries on obviously to all 6 results. And then what you'll see is here I've got this command here called legend. Okay, and this is going to put a legend so that I know what graphical output in terms of system response corresponds to what RC value. So in this case, you can see RC equals 0.5, 1, 1.5, 2, 2.5, and 3. You've got to do it in these little quotation marks with a comma there. Make sure when you actually do this in yourself, though, when you do this in, and one thing I'm just going to say, make sure you do this in MATLAB Editor. When you do this, make sure that this is actually on the same line as here, otherwise it'll throw up an error in MATLAB. Okay, and then for, as I just said, end. So it's effectively just running a loop of these 6 different values through this simulation, and then I'm putting a legend on just to map the results. So if I go here, this is what I get. So you can, in your own time, you could look again at this equation and look again at these RC values here. And what you'll see is RC value of 1. That's initially what we had when we did the hand sketch. And you can see here, if we were to look at this, okay, we said at 95% or 0.95, it was at 3 seconds. As you can see there, around 3 seconds, that particular one where we've got a time constant of 1 is at 95%. And then as you expect, if you increase the resistor or the capacitor, the system response, or the time that it takes to charge the capacitor, is going to increase. So you can see as a result, RC in this case is 3 on this one, and you can see the system response is much, much slower. It's taken approximately, I don't know, 15 seconds to get to about 95% of the final response, whereas in the case of having an RC, a time constant of 0.5, it was getting there in just over 3 seconds. So you can see, obviously, the relationship that we explored earlier, we spoke about earlier, is obviously true, and as you'd expect. So it's taking longer for the capacitor to charge with an increased resistor or capacitor value. So in summary, a first order differential equation has been given for resistor, capacitor, RC circuit. Go away and read up more on that circuit if you want to do so. It's going to demonstrate how to convert this into transfer function form, and then how to understand the system properties based on the standard form. So in this particular case, it was looking at tau is equal to RC, and how this effectively corresponds to the system response, and different values will give faster or slower system responses, or i.e. charging of the capacitor value. It's been demonstrated how using Matlab for modeling simulation has been used to explore the different parameters of the RC circuit, so effectively the time constant. So I hope you found this video useful. Please contact me if any questions.